are three pillars, so-called pillars of the Big Bang model that we cosmologists adhere to and use in our daily work to gain more and more credulity in the model itself and to also test it for its cracks, flaws, and foibles. Those three pillars on which our modern cosmological model rests are the expansion of the universe, the Hubble expansion of every single galaxy with a tiny handful of exceptions. 500 billion galaxies are all receding away from us. We want to be able to explain that in a self-consistent, coherent conceptual framework. The origin of the primordial photons that I study, called the cosmic microwave background, have to be explained and are explained in the context of a hot Big Bang. And last but not least, a topic we haven't really touched upon in this channel, at least in the depth that we're going to go into today, is called BBN, Big Bang Nucleosynthesis. What does that mean? Well, we know we're made of matter. We know there's a lot more non-matter like us in the universe, so-called dark matter. We've talked about that in many episodes, and we'll continue to do so. But the Big Bang nucleosynthetic predictions predict how much ordinary matter should exist in the universe. Matter such as the kind that we're comprised of. Primarily, the primordial elements, hydrogen, helium, and their isotopes, deuterium, tritium, helium-3, give us great bounds and significant constraints on what the properties of the early universe were like. The Hubble expansion says that every one of these galaxies in the Hubble deep field are expanding away from us and every one of them. So there's no center of the universe, there's no place that can call itself the origin point of the universe. We've long ago dispatched with those notions. That is a pillar dating back to the original piece of evidence from Hubble and from Lemaitre theoretically and Alexander Friedman, that the universe was an expansion. It was not static. It could not be held to be consistent with a static universe. Next, in 1965, Penzias and Wilson discovered a fossil relic in the form of photons that were also highly redshifted, dating to an epoch when the universe was only 371,000 years old. Now, where did those come from? Well, the galaxies that I show you here came from the fluctuations in space-time curvature and the agglomeration of ordinary matter in dark matter reservoirs that were laid down by curvature perturbations in a primordial scalar field, perhaps inflation, perhaps another field. We'll continue to talk about that on this channel. But the primordial CMB fluctuations provided the seed nuclei and nucleating sites where ordinary matter could form into galaxies and clusters of galaxies after accreting onto dark matter, which had to precede the ordinary matter's existence. So these are fossil relics. One is a fossil expansion of galaxies that are quite ancient. Another is even more ancient, photons from the CMB. And today we're going to talk about the formation of the elements and how they lead to this picture of the cosmic web, cosmic pattern of galaxies, what they are not, how they are located is a direct tracer of the properties of the ordinary matter. After all, these galaxies in this millennium simulation are tracing the position of ordinary matter, protons, neutrons, the crouton. These ordinary matter particles conglomerate where there was dark matter. That dark matter arose in certain locations over other locations because of the presence of curvature fluctuations, creating gravitational potential wells for the dark matter to fall into, which then accrete ordinary matter, which then make CMB photons have a harder time climbing out of the potential wells established early on in the universe's history. Eventually, that matter, the ordinary matter, ignites and forms galaxies. But where did that ordinary matter come from to make this incredible tapestry, this rich cosmic web? The formation of the first elements, the lightest elements, the primordial elements of nucleosynthesis. So the pillar that we're talking about today is called BBN, and we have accounted for the others in terms of a pre-existing amount of matter. We have to have an accessible prediction to compare with accessible observational data. And you've often heard it said, and I said this to Neil deGrasse Tyson when I was on his Star Talk podcast, I said Carl Sagan used to talk about how we're all star stuff, which is true for the heavy elements in our bodies.
I see what you did there. You said boom.
Boom, yeah, I
see
gotta
what
put
you
the boom
did
in
there.
there. Gotta put a bang in there every so often. The calcium in our bones, the iron in our blood. But where did the ordinary matter come from that makes up 70 or 80% of our body by mass? Some more than others. But that mass is in the form of hydrogen. That hydrogen didn't come from stars. It came from the Big Bang. and we can account for it and test our model of cosmogenesis by using observations of how much hydrogen remains to this very day. So when we look at primordial BBN nucleosynthesis, what we want to see is what evidence is left over from these early epochs. This is the process of fusion of protons, of neutrons, to form deuterium, heavy hydrogen, tritium, even heavier hydrogen, and heavier elements like helium, helium-3, etc., lithium. They have very few numbers of protons, and that is going to be associated with their placement in the periodic table, but also their mass. And their mass is determining their energy, their binding energy, via E equals mc squared, the most famous equation in all of science. The formation of these light elements is not perfectly efficient. In fact, fusion gives off heat, which is why we think we can use fusion to power our electrical needs on Earth. That's the backbone of the fusion reactor dream or goal. To date, we have not been able to provide a sustainable solution for electrical power using fusion, bringing together two lighter things to make a heavier thing with some binding energy left over in the form of heat or photons. Those photons then later heat up the remaining protons, neutrons, and electrons that exist after the first few seconds after the Big Bang. And that heat then persists as the universe expands, and that heat cools off from very, very strong hard X-rays and gamma ray wavelength radiation to the CMB radiation that we observe today after expansion of many thousands and millions of times in our universe since the first few seconds after the Big Bang. So when I teach my students this, we are archaeologists, I say. We are going back in time to an early epoch that we can test the properties of by looking at the relics that have traveled through space and through time. Some of these objects are still very far away from us, but my colleagues with their powerful telescopes and their mighty brains have devised ways to use that information that we see through telescopes and use them as time machines to go back to this epoch of nucleosynthesis. And then my colleagues in the cosmic microwave background experimental regime, we work on detecting the photon left over, and the combination of the amount of photon relics plus matter relics tells us everything we need to know to test the Big Bang's predictions of a hot, dense, early configuration of the universe. When we talk about the radiation in the universe, we know that the number of photons per cubic meter, centimeter, megaparsec all decrease as the size of the universe increases. As you increase or double the size scale of the universe, the scale factor A of t, that tells you that the volume increases by a factor of 8, 2 cubed. Now, photons and other forms of radiation also suffer an additional effect, which is that their energy gets redshifted because their wavelength of light gets redshifted along with the expansion of the universe. Putting these together, in the earliest epoch of the cosmic history, the universe was evolving as an expanding, purely radiation-filled cosmos. Now, when we look at the early universe, we can then make accurate predictions of how fast it was expanding. From the expansion rate, A of t, its derivative, A dot, or the time derivative of A, we can get the Hubble parameter at any time in the universe's history. The Hubble parameter evaluated today is the Hubble constant, but we can accurately test it and trace its history and calculate how fast was the universe expanding at extremely early times. Noting that the universe is still filled with photons left over from this period of time, this first few minutes after the Big Bang, we can calculate the abundance of radiation and what it must have been like, how hot this radiation must have been like when the universe was 1 trillion times smaller than it is today by volume. To do that, we can ask how hot was a given photon in the universe zipping and buzzing around. That is easily calculated from Planck's black-body radiation law, and when we do that, we get an energy scale. And that energy scale depends on time because the universe is expanding and the photon wavelength is expanding. So each individual photon's energy will drop as the universe doubles in size, it will drop in half. That is simple photon physics in so-called redshifted or expanding cosmological scenarios. So at 1 second after the Big Bang, the universe had a characteristic temperature associated with a characteristic energy of about 3 mega electron volts, million electron volts. And for reference, an electron volt is the amount of energy that you need to accelerate an electron to give it a potential of 1 electron volt. Now, that's not very helpful or very useful, but you can think about it in these terms. To take a single hydrogen atom and hit it with a photon, such that that atom of hydrogen dissociates, ionizes into a proton and an electron, you need to zap it with only 13.6 electron volts. You may remember that from high school chemistry. I sure do.
Well, maybe.
Maybe.
That amount of energy pales in comparison to 3 million electron volts was the characteristic energy of photons at this time, meaning that photons could easily blast apart any atoms, explaining why atoms didn't exist. Now the question is, did nuclei exist? The binding energy of nuclei are much higher than the binding energy of a proton to an electron that we call a hydrogen atom. Now let me give you some characteristic energy scales. The CERN Large Hadron Collider, which is directed by my fellow narrator, Fabiola Giannati, in Galileo's dialogue on two world systems. You can get a link in the video description, briankeating.com/dialogue. You can get your own copy. And here, Fabiola, the director of CERN, she oversees this massive collider that can replicate the conditions in the early universe at certain times. So she can replicate the universe with her colleagues. If you extrapolate back the temperature law that I show up above, as a function of temperature, the temperature goes up as the square root of time as you go back in time. And so she can actually access energies that are 7 trillion electron volts. That's over 2 million times larger than the energy the universe was at 1 second after the Big Bang. So you square that million, you get roughly a trillion, and you work out the math exactly, and you get that she could maximally probe with the most powerful collider on Earth an epoch in which the universe was about 1/10 of a trillion of a second old after the Big Bang. But that pales in comparison to what we are attempting to do with experiments like the Simons Observatory, which is to go back some 10 to 20 orders of magnitude more in our search for primordial B modes, as we've discussed in previous videos. So how far back could you possibly go? Could you go back to the Planck era? Well, that would correspond to a time and an energy scale that is far in excess of what you could detect here or use here on Earth. So there's no hope to build a particle accelerator to access the energy scales that we can get to with cosmic microwave background radiation experiments or thereabouts. So let's do some simple nuclear physics. Let's talk about the lightest elements on the periodic table. Let's compare them to other elements in the periodic table. So atoms, which are just bindings of protons to electrons with neutrons in the nuclei to electrons in the outer orbitals, those have characteristic binding energies of the electron volt scale. So to ionize a hydrogen atom, you need 13.6 electron volts. Helium has 2 protons, so a single electron is more tightly bound because there's more Coulomb or electrostatic force. So you need almost twice as much energy to zap off a single electron. Cesium and other things have screening effects, and it makes it easier to actually eject an electron in a cesium atom. So you can calculate the characteristic energy scale of a chemical or nuclear process by its binding energy. To bind an electron, you have to ensure that photons no greater than 13.6 eV are floating around, otherwise it will get dissociated. To bind the most simple complex nucleon, the deuteron, has a characteristic binding energy as well. So these nucleons, when we come together, we make nuclei. Those nuclei have 2 properties that are associated with them. Their atomic mass number, which is the number of protons plus the number of neutrons, symbolized by capital N for the neutrons and capital Z for the protons. I don't know why it's not P, but it's not. The atomic mass number A is Z plus N. Very simple math. So Z determines which period in the periodic table it's in, and the number of isotopes are determined by how many different permutations of neutrons still have the same atomic number. So you still have the same atomic nuclei, the same number of protons. For all intents and purposes, we will only concern ourselves with the first, say, 5 or 6 elements on the periodic table, because those and their isotopes, and there's several isotopes of many of these nuclei, they give us enough information to constrain the properties when the universe had this characteristic energy of about a few MeV, million mega electron volts. The nuclear binding energy for deuterium is the first one we're going to look at.
Binds the galaxy together.
We're going to ask, when you bind together a nucleus, how much energy would be released if you were to break it apart? And if we look at the lower right corner, this is taken from my past guest and friend Barbara Ryden's wonderful book, Introduction to Cosmology, you can calculate what is the binding energy, B, divided by the atomic number. That tells you something about the stability of that nuclei. That nuclei will be determined by sometimes having enough neutrons to keep the number of protons bound stably, because you have to supply an additional force to overcome the Coulomb repulsion between protons. So helium, for example, has 2 protons. How could you possibly get 2 protons to stick together if they have positive charges? They should repel. The answer is you need some neutrons around. And those neutrons have opposite isospin charge, if you like, and that allows the up quarks and down quarks in the right configuration to attract together additional protons to the neutral neutrons by going inside, if you like, detecting the swirling process of quarks and the binding of quarks, and that's what causes them to stick together. So stable nuclei are plotted here as having solid dots. There are isotopes, and there are unstable nuclei plotted here as well. And when you get to something more massive than iron, that is the most stable atom in terms of the maximum binding energy per nucleon. Once you try to exceed that, you have to then supply more energy to get fusion to occur than you actually get released. You do get energy released from fusing together, say, nickel 62, but actually the amount of energy you get out far pales in comparison to the energy you put in. Therefore, there's not enough heat produced by the star's core when it's synthesizing this, and so it eventually explodes and blows apart in what's called a type 2 supernova. The meteorites that I like to play around with and often give away if you join my mailing list, briankeating.com/list, so people can win a little scrap of an exploded star, which has nickel, iron 58, and other isotopes in it. Not dangerous, don't worry, but those come from the fragmentation explosion of a gravity bomb that we call a type 2 supernova. And that's what happens when you try to make heavier nuclei. Now let's go back. We're not talking about stars today. We're not talking about heavy elements like iron. We're talking about the lightest elements on the periodic table. So nuclear fission occurs, typical binding energy of about the MeV scale, less than about 10 MeV, millions of electron volts. So we can form deuterons when the characteristic photon energy is less than the binding energy of that nucleon. And the nucleon has a binding energy of about 2.22 MeV. So as long as the temperature of the universe on average is lower than the binding energy of deuterium, or these deuterons, the universe can form copious amounts of deuterons. However, eventually the universe gets quite cold and there are no photons with that temperature to break apart any deuteron. So eventually this is going to stop, but there are other reasons why it stops even before that. That sets the amount of deuterium that remains in the universe after a few minutes after the Big Bang. And we can observe and go out in the universe and count large distances, high redshift equivalently, or early look-back times. We can detect these deuterons at high redshift. Then we can use that to compare with what the predictions would be based on the observation of the amount of photons and protons and neutrons in our universe today. So the binding energy corresponds to a temperature of about 3,700 degrees, almost 3,800 degrees, and that's an age in the universe that's about 300 seconds after the Big Bang.
That was fast.
But we're talking about 5 minutes after the Big Bang. The deuterium can form in large amounts. Now that assumes that there are enough nucleons of the neutron type to exist. And I've talked in this channel about the decaying of neutrons. Neutrons decay in about 800 seconds on average. So that means by the time the universe cools enough that you can start making copious amounts of deuterium, there have been many decayed neutrons. Protons don't decay. The neutrons decay, and so there's not that many of them left. Almost a full half of the total amount of neutrons are gone by the time the universe is cool enough to start forming deuterium. So it's actually said to be quite inefficient. The universe has only about 1/4 left over of these deuterium is produced, and so we actually have about 3/4 of the universe just in single protons, which we call hydrogen. Now, another element that we can look at is element number 2 on the periodic table, helium. Helium has a symbol in cosmology called Y.
I don't know why it has that symbol, but it does.
And so we can calculate how much helium is left and compare that to the abundance of helium that we see in the universe, taking into account that stars like our sun do produce helium. That's how helium got its name. Helium stands for Helios, the Greek god of the sun. How did they discover helium on the sun before it was discovered on Earth? They went at night. No, that's an old joke. Some helium that's made, and if you go through the calculation precisely, we predict a primordial abundance of helium of about 25%. It's actually a little bit less than that. So we have 75% hydrogen, about 24% helium, and that means everything else that we're made up of in the entire universe by mass is less than 1% of all the mass density and ordinary matter in the universe, forgetting about dark matter, which dwarfs ordinary matter by another factor of 5. What we're made up of is so irrelevant to the overall chemistry and mass in the universe that no amount of overeating and binge eating will protect us and prevent us from being completely irrelevant on a mass scale.
Somebody needs therapy.
So when we look at how the energy of deuterium can be converted to a binding energy, meaning that if you zap it with enough energy, it will shatter apart into proton and to neutron. Same thing can hold for an individual neutron. You can zap a neutron apart. A neutron has a binding energy, if you like. The neutron decays in about 880 seconds. So in about 300 seconds, we have a decay of nearly half, or let's call it close to a third of an entire half-life. So that doesn't mean a half or even a third of a half have decayed. We can calculate it exactly. But we can look at how this process of a neutron decaying into a proton, electron, and electron antineutrino for lepton conservation, how that is associated with a binding energy. And we can calculate how that occurs. And that tells us about the stability of neutrons, and we can associate a binding energy with that as well. So we can use that factor and calculate the amount of neutrons that are existing. And that'll take us from 300 seconds back to about 1 second in the cosmic history, when there was enough energy to shatter apart neutrons into protons and neutrons and electron antineutrinos. So at times much, much earlier than the half-life of the neutron, there were about 1 neutron for every 5 protons. So that means at most, you could make a neutron plus a proton, which we call a deuterium nucleus, and there'd be left over 4 unbound protons. So there's almost no fusion of most of the protons in the universe by number. So when we look out at the universe, we find, if we do the calculation correctly, we can predict how much helium there should be. Very rough estimate gives you an estimate of about 1/3 using the calculation. I'll leave it up there for the aficionados to go through. And if we calculate the fraction of the neutrons that are still remaining, we do this calculation accurately, we end up with a fraction of about somewhere between 0.24 and 0.245-ish. So it's extremely accurate. Then we just have to go out and measure before stars started to form, these vast Lyman alpha clouds, clouds of hydrogen and helium that were existing after the Big Bang. We can measure that. There's also another isotope of hydrogen, which is even more exotic. It's actually radioactive, called tritium. I don't have access to that. It's incredibly dangerous, so I won't be doing any experiments with that. So what we want to look at is the abundance at these different signposts, mile markers. Not millions of years ago, not billions of years ago. We're talking about 13.8 billion years ago. 1 second after the Big Bang is 1 milestone. How many neutrons were left after being dissociated perhaps by high energy photons. Then at 300 seconds, and then finally, looking back at their leftover protons and neutrons and electrons that were in existence when the CMB itself formed. So we do that, we can calculate very, very accurately how much there should be left today. This abundance shows the amount of energy density in the form of mass for different objects in the universe, starting, not including hydrogen, because hydrogen will be off the charts here. The first in the split graph shows you a very large abundance of helium, helium-4. There's also helium-3, down much, much lower abundance. There's deuterium, which is the 3rd most abundant of all nuclei in the early universe. We can compare that. And then we can go even further down to look at lithium. And that gets really hard to look for primordial amounts of lithium, but we show this as a function of the baryon to photon ratio, which is indicative of the fact that the universe was producing copious amounts of energy. When these light elements are fused together, they give off energy. That energy is in the form of photons. Those photons ride along and expand along their wavelengths as the universe expands from 1 second to 380,000 years after the Big Bang. So, in summary, the primordial relics of photons and the earliest combinations of protons and electrons are the most ancient fossils that we can detect and measure to this very day. We look at the abundances of these different elements in the universe, and we correlate that to predictions of when they left the nuclear furnaces that produced them. When we go out in the cosmos, we can then compare the abundances at very high redshift, which is not equal to looking back at 1 second or even 371,000 years after the Big Bang. But we can go back as far as we can, make the assumption that there are no stars producing these other elements, like deuterium. Certainly stars aren't really producing deuterium, but they do produce helium. Before the first stars were formed, we can look at those heavy gas clouds, look for their material composition, compare that with the results from the theoretical models that we've just talked about, refine our models, and then eventually we will get to a place where we can predict the abundance of all the ordinary matter in the early universe and can then use the abundance of ordinary matter to then trace the properties of dark matter, which then traces the properties of structure formation, of curvature, and eventually perhaps of inflation itself. That's for a future video. For now, Brian Keating thanking you for attending this class for course credit in what I call 30-minute thesis. If you like this video, make sure to click here for another video in the 30-minute thesis collection. And don't forget to subscribe.